So hi, we're gonna be talking about virtual coach, where we are trying to help amputees with the adoption of their prosthetic arm. So the motivation behind this is that it's very hard for the amputees to sort of adopt to their new prosthetic arm. They find it really hard initially, and they are not really able to control it in the way that they want. So, the hypothesis behind this is that there's this experiment and research which shows that the human brain can sort of adopt a, a fake arm. So, in this experiment, it basically says that if you have a fake arm and if you have an actual arm, you can trick the human brain into believing that the fake arm is yours. So we are sort of using this hypothesis to go ahead with our goal of helping the amputees with the adoption of their prosthetic arm. So what what happens is when you're communicating with when you're trying to when you're sending signals to your arm is that the brain sends myoelectric signals which sort of go through your arm, and then you are able to control your wrists. You are able to make all the gestures that you want. So we are testing on 7 gestures, including like wrist flexion and wrist extension, and we are detecting that using our model. So we started by collecting like a data set from 20 users, and our basic architecture includes the prosthetic arm or the prosthetic sensors which the users would wear. We would test it on healthy users and hopefully use transfer learning to help amputees with their actions. We have a machine learning layer which will basically use the machine learning model which we trained from our participants, and use the inferences to predict what the amputees are trying to do. We have the cloudlet since we want the the sensors are not compute intensive enough, and not like they don't have enough power resources to run our machine learning model. So we basically have a cloudlet and we use edge computing, and our sensors act as a thin client. So all the compute happens in the cloudlet, and we just transfer all the data back to our sensors where it can be used. And finally, the participants play games like 1942, and it can be extended to Flappy Birds, where they do a bunch of actions controlled by their arm. Varun can talk more about like the machine learning aspects.
So as for machine learning, we had two kinds of data. One was collected at 1000 hertz, and the other one was downsampled to 40 hertz. We have this differentiation because the data we collected at 1000 hertz could not be streamed from the device onto the cloudlet at enough speed, and it led to packets being dropped. So what we did was we trained our model on the 40 hertz data. We tried two kinds of approaches. We tried the traditional machine learning approach, where we did some feature extraction using temporal domain decomposition and temporal and spatial domain features. We tried this on 1000 hertz data as well as a bit on 40 hertz data. In the end, what we ended up going with was a random forest model with 300 decision trees. Which ended up working best for our use case. We also tried deep learning models, which we trained on SEMG features, which are basically channel frequencies concatenated together across time. So we trained an LSTM model on these features in order to capture the temporal, the sequential nature of the data. Um, we also use this model in order to be robust to user-wise changes in channel activations. So I'll hand it over to Kevin to talk a little more about the analysis part.
Hey, so I essentially talk about the three graphs that we have here. The first graph, or the first pair of graphs, show the box plots of the raw values we're gathering from the device for two different users performing the same movements. Perhaps it's a bit too far from your perspective, but what you essentially see is that the values for the same movement for two different users are very different across each channel, meaning it is very difficult to know, if you just look at these graphs alone, what movements, if it's the same movement, those two users were performing. So what we essentially wanted to do is to extract features from those raw values that would be better able to capture what movement a user is is doing and have those features ideally be very similar for the same movement across different users. So as Varun explained, we trained a random forest model for 15 users and tested on 5 other users for the 7 movements you can see here. So essentially the rest position, opening your hand, closing your hand, wrist flexion, extension, supination, and pronation. And as you can see on this graph, is that as you increase the number of people that are included in training the model, the accuracy of the test accuracy essentially linearly increases, which leads us to believe that if we had more time, we would and had the ability to train on more users, we would be able to get an even higher accuracy than the around 65% that we have right now. So in the future, we definitely want to collect data from more users, try newer machine learning algorithms, and also actually test on actual amputees and see whether our algorithms perform equally as well for them as they do for the healthy patients that we tested with. Thanks a lot.
So what we're doing here is using Kevin's hand motions as directed by the band over here to move the sprite on screen. As you notice, his motions are from the arm, but the only data that we're getting is from the elbow, which will be similar to what we'll get from actual amputees. So this is a demonstration of how a prosthetic device could work. So, so as you see, Kevin is making this motion in order to turn left. He's making this motion to turn right, and he's making this motion to shoot. So also, one thing to notice is all the machine learning and all the processing is being done on the device. So it's like a cloudlet model. There is no compute on the sensor on the sensor device itself. It's all done by remote machine. So.